Hello friends and welcome to another lecture on chemical engineering thermodynamics. Now today we will take a paper which has come from a question rather which has come in chemical engineering thermodynamics 1 paper of Mumbai University. This had come on May 19 and the question was 5B. The question is on your screen. Calculate the enthalpy and entropy departures of ethane at 400 Kelvin and 1 megapascal using van der Waals equation of state. The data has been presented to you. Now a volume has been given to you 3.21 into 10 raised to minus 3 meter cube per mole. Now this really does not say whether this volume has been calculated using an ideal gas state or a real gas state. So for now we shall not consider this and we should find out the volumes and solve it. Now the formula for residual enthalpy and residual entropy are already there on the board. And as you can see that I have always suggested that students should commit these formulas to memory because these formulas can be applied to any cubic equation of state. So what do we require? It's very simple that whenever we are solving a van der Waals equation of state problem, the information that we require is first for A and then for P. That is the van der Waals constants. We will require this in solving the problem. So this is going to be 27 by 64 into 8.314 into the temperature of critical temperature, that is 305.43, the whole square, upon 48.84 into 1000, and B will be 8 into 48.84 into thousands, since 100, since we have to take it in kilopascals. That's not 1000. Let me make a correction here. Yes, it's 100 since we have to convert it into kilopascals, and this is going to be 8.314 into 305.43. We have the values of A now as 557 kilopascal meter raised to 6 by k mole, and the value of B is 0.065 meter cube per k mole. So these are the two values we get for A and B. Now, after this, we need to fix the standard state. Okay. So the standard state we are going to take is the lower limit for the integral for lower limit, that is V infinity. So that we take it up as V, okay, that state we take it up as the pressure at that state is equal to 100 kilopascals or 1 bar. Now anybody who is reading your problem or reading your solution should know what is the standard state you have taken for the lower limit of the integral. Okay, the temperature obviously for this is 400 Kelvin. Therefore V1, that is the lower limit of your integral, is going to be is equal to 8.314 into 400, that is RT, upon P, that is 100. So this is going to be equal to 8.314 into 400 divided by 100. So that's 33.256. So that's V1 is equal to 33.256 meter cube per k mole. Okay, so that's it. 33.256 meter cube per k-mole. So that's V1. Now we have to find what is V2 and what is Z. So V2 is going to be the volume at the upper limit, and that volume is going to be at a pressure of 1000 kilopascals, that is 1 megapascal. So 1000 kilopascals, and a temperature of 400 Kelvin. Now this volume will be calculated using the van der Waals equation of state. So what do we have here now? P is equal to RT upon V minus B minus A by B square. This is the van der Waals equation of state. Now we just replace V is equal to ZRT by P. So what do we have now? P is equal to RT ZRT by P minus B minus A by V square. So the V square now gets replaced by Z square R square T square over P square. Now the RHS is equal to, if we remove RT by P, so we are going to have P on the top here, and we have removed RT, so this is going to be Z minus B, where B is going to be equal to BP by RT, and this will be A by Z square. So that's capital A, that is capital A by Z square, which is going to be equal to A, capital A is nothing but A P by R square T square. So therefore P is going to get remain common here, and P is here too. So the P gets cancelled off, and we are left with 1 is equal to 1 by Z minus B minus A by Z square. Now writing the cubic equation in Z makes it simpler to solve it. So now what we have is Z square into Z minus B is going to be equal to Z square minus A Z minus B. That makes it Z cube minus B plus 1 B plus 1, yes, so into Z square, so this is, yes, B plus 1 Z square minus, so that becomes plus AZ minus AB equal to 0, right? So this is the equation that you have. So slightly we have to take care while writing this down. So this is Z cube, this is Z square minus B, then we have Z square here. So when brought here, it's going to be minus 1, the minus sign gets common here, minus AZ, when we get it here, that becomes AZ, okay, and AB, fine. Now what we need to do is we need to find A and we need to find B. Now both of these are dimensionless. So A is going to be nothing but 557 into 1000 by 8.314 into 400 kilopascals, the whole square. And this will be equal to 0.065 into 1000 divided by 8.314 into 400. That will give us A as 0.050, 0.050, and B as 0.1954. So 0.01954. Mind you, both of these constants are dimensionless, right? So we have A and B. Now, if we have to solve this cubic equation of state. So that's going to be Z cube minus 1 plus 0.01954 Z square plus 0.050 Z minus 0.050 into 0.01954 is equal to 0. Now let's solve this cubic equation to get the values of Z. Therefore, let's take the calculator and go to mode 5 and then 4. So the first constant is 1. The second constant is minus 1 plus 0.01954. That's it. And the third constant is 0.050. That's right. And the fourth constant is minus 0.050 into 0.01954. And that's minus 0.99.77 into 10 raised to minus 4. That goes in. And we have the first value of Z. So Z1 is equal to 0.9689. So if we round it off, this is going to be 0.9690. So that's going to be 0.9690. Okay, Z2 and Z3, let's find out. In all probability, it's going to be a complex conjugate roots, but still, to prove it, yes, it's a complex root, as you can see here on the calculator. And this too is a complex root, and it's the complex conjugate of Z2. So that being done, we have the value of Z. So we have to reject Z2 and Z3 and only take Z1. So now we get V2. Okay. So now V2 is going to be 0.9690, that is Z, into 8.314, that is R, into T, that is 400 Kelvin, by the pressure, which is 1000. So this we get as 0.9690 into 8.314 into 400 divided by 1000. That is 3.2225. That is 3.2225 meter cube per K mole. So now we have the upper limit of the integral, that is 3.2225 meter cube per K mole. Now let's find out what is delta HR. This is going to be RT into Z minus 1 plus integral V1 to V2 T dou P by dou T at constant volume V minus P dV, right? So we need to find dou P by dou T at V for the van der Waals gas, and this will be nothing but R upon V minus B. Therefore, delta HR is RT Z minus 1 plus, if we replace this in here, so we are going to get V1, V2, RT, V minus B, and we replace P here. So minus P is going to be minus RT, V minus B plus A by V square. So this both gets cancelled off. And finally, in the integral, we are left with A by V square. So let's now substitute for the values here. That's going to be 8.314 into 400 into Z 0.9690 0.9690 minus 1 plus integral of A, that is 557 over V square, and the lower limit is the ideal gas volume, which is 33.256. So that's 33.256, and the upper limit 3.2225. 3.2225. So we have it, and now let's start and use our calculator to do the number crunching. Let's not simplify anything. The calculator will do it. 8.314 into 400 multiplied by 0.9690 minus 1, close the bracket, plus start the integral. In the integral we have 557 divided by alpha x square, right? And now we put the upper and the lower limits, that is 33.256, and the upper limit, that is 3.2225, and is equal to, that's minus 259.1919. So delta HR is equal to minus 259.1919 kilojoule per k mole, right? So that is what we have now. Now we need to calculate what is delta S R. That's going to be equal to R ln of Z plus integral V1 to V2 dou P by dou T at constant volume V minus R by V dV, right? So we can write delta S R as R ln of Z plus integral V1 to V2. So that's going to be R V minus B, replacing dou P by dou T at V, minus R over V, and that's dV. Let's have a look here once again. See, dou P by dou T at V is R V minus B. So that's what I have replaced off here. Therefore, delta SR, now we can put in the values 8.314 into ln of 0.9690 plus integral of, okay, 33.256, 33.256, and then the upper limit is 3.2225, 3.2225, and then we have R, we can remove it common here. So let's do that. We can remove R common here. So let's put a small plus here and write 8.314. So we can write this as 1 over V minus 0.065, that is B. So that is your value of B here, the small b, that's here, 0.065, okay? Yeah, minus 1 over V dV. So we have it here. Now let's calculate the value of delta SR using the calculator. Let the calculator do the number crunching. So that's 8.314 into ln of 0.9690 plus 8.314 into, start the integral, and then we should have brackets in the integral because there are two members in the integral inside the integral. So we have 1, the first fraction is 1 divided by alpha x minus 0.065, and then minus, start the bracket, start the fraction once again, 1 divided by alpha x, where x is the replacement for v. Okay, so the lower limit is 33.256 and the upper limit is 3.2225. So I'll make that correction later on, and let's do it, is equal to, that's minus 0.4149. Okay, 50. So ultimately we can round it up to 0.4149, and it was 6, so 50, 0.41, 0.4150 kilojoules per k mole Kelvin. So that's the second value. So that's the value of delta SR. So as you can see here, I have demonstrated how to solve this problem simply by even mugging up the formulas. You just need to know the basic definitions of residual entropy and residual enthalpy, and you can get the values by using the calculator. Right? No calculus is involved here. Absolutely no integration was done here. All the integrals were solved by using the calculator itself. Now, remember, this method which I have proposed here can be used for any cubic equation of state. Tomorrow, if this question is asked using Redlich-Kwong equation of state, the methods are going to be the same. The process, the steps are going to be the same. So that was all. I would again like to request all of you to subscribe my channel and share it and popularize it as much as possible. My current subscription base is 591 and I need to hit 1000 to make this entire project viable. I need to hit 1000 subscriber base. So I request all of you who are watching this video to promote this video. People who like it, I would just ask them to subscribe it off. Promotion and subscription is going to help me a lot. Thanks a lot once again. Keep watching, and in the comments do write if you find any problem with the lectures, and also write if you want any problem to be solved. I shall prepare a video and put it up for you. Fine guys, have a great day. Bye.